Forest mensuration, lecture number 18. In this lecture, we are going to learn about the tree stem form. Tree stem form is very important because it will let us to calculate the volume. So volume is very important part. So tree form factor, we can also say tree stem form. What is the form? It is a stem profile. Tree stem form is defined as the rate of taper of a log or a stem. So we see here different type of forms are here. They are a bit cylindrical. Here you can see it is a paraboloid. Here it is like a cone. So it is here irregular, you can see. There are different forms of a tree, different shapes of a tree. So here we'll learn about the tree stem form because this will help us to calculate the volume. So it is defined as the rate of taperness of a log. Rate of taperness, as we go from base to the top, how the tree tapers. At the base it is wide, slowly as we go along the height, the rate stem tapers down. So we'll study about the tree stem form. So taper is the decrease. You can see it is a decrease in diameter. Here diameter is good enough. As we go in the top, the diameter slowly decreases. So taper is the decrease of diameter of a stem as the tree from the base to upward. Before we study about the form, we will have some concept about the moment of inertia. What is moment of inertia? So moment of inertia is very important because this will let us to know about the shapes of our tree stem, how it changes. So we can say it is also a measure of resistance against the force. So it is the measure of the resistance against the force. What is the force? Force may be wind, force may be the weight of a stem or a crown in the tree. So we'll come and learn about this one. What is moment of inertia? There are two types. One we call polar moment of inertia and other we call moment of inertia. In polar we consider the z-axis. In moment of inertia we will take two axes, y-axis and x-axis. Change in its rotation, we can say it is in the rotation like this, torsional, or capacity of a resistance to the bending like this. So there are moment of inertia. First we'll discuss about the polar moment of inertia. Polar moment of inertia is the measure of resistance against the force applied to the changes in z-axis. So this is a z-axis. If this is a log, this is the z-axis coming from the center. So the changes in this z-axis. So in many books it is this calculation has been given of a moment of inertia, has been calculated. Ultimately we get the diagram IZZ. This IZZ is pi d to the power 4 divided by 32. We also call it torsional constant. So this is polar moment of inertia. Now next is this polar, and this is moment of inertia. What is moment of inertia? This we'll take it from here. This moment of inertia, this circle. This is the moment of inertia of a plane area is normal axis to the plane is equal. This is equal to the sum of two mutually perpendicular axes lying in the plane. That is, you can see this is x-axis, x one axis, this is y. So they are passing what? Mutually two perpendicular axes. So this is sum of two. This is sum of two. What? The moment of inertia of a plane area is normal axis to the plane area is equal to the sum of two mutually perpendicular axes. You can see this IZZ. This is sum of two mutually perpendicular axes. This one. So if this is 32, this will become here 64. So polar moment of inertia and moment of inertia just is a, we should understand about what does the moment of inertia means. What does the moment of inertia means? Again, I'll repeat that polar moment of inertia is the measure of resistance against the force applied for the changes in this z-axis. So this is the measure of the resistance against the force applied on the changes in, suppose this is on the z-axis, whatever the changes comes here. And this resistance, this moment of inertia is resistance against the force applied to the changes in x and y axis. We'll take x and we'll take y axis, these two. Okay, this x and y axis. What is the changes in x? Like we are having a torsional changes. Pi. Now pi is the ratio of a circle's circumference to its diameter. Now when we take cross section of a tree, generally we calculate the sectional area either by pi d square divided by 4 or pi r square. Now if we take pi d square divided by 4, means when we take diameter, then this is the formula, pi d square divided by 4. But when we consider radius, then it is pi r square. We do it for when it is a circle. This is the diameter of a tree. Okay, and pi is the ratio of a circle's circumference to its diameter. What is pi? Is 22 by 7. So what we get the pi value, we get it 3.1428. Generally all tree species are not circular, true circular. It may be ellipse or it may be irregular. So we take two diameter, either we take two diameter or we may take semi major axis or a semi minor axis. Now when we take this axis, let's take a major axis of this dia, we can say D1, or we take it this one as a D2 minor axis, or we take a semi. When we take semi minor axis, we may say it is a radius, and when we say semi major axis, we also say it is a radius. It may be A or it may be B. A is semi minor axis, this is a minor axis, and this is the semi major axis, may be radius. So we, as to calculate the cross section of a tree, sectional or a sectional area, or we also call it a basal area. Basal area. So this is ellipse. When we take a ellipse, by ellipse means when your tree is not a true circle, it is somewhere like that. It's called ellipse. So ellipse is, how we will calculate? By formula 1 is pi a plus b divided by 2 whole square. This is an average we are taking. And other formula is a square separately plus b square separately divided by 2, then multiply by pi. So these are the two formulas to know the sectional area, cross section of a tree, or we also call it a basal area. The third one is girth. By girth, how to calculate the basal area is g square by 4 pi. We'll get the basal area, or we can get the cross section of a tree or a sectional area. So before that, we'll understand the relationship of diameter and girth. So diameter is girth divided by pi, or g is equal to pi into d, and pi is already, I told you, is 3.1428. So girth is approximately 3 times the diameter. So hence girth is equal to pi d. So whenever we have diameter, so whatever we have a diameter, it is around, when we take the girth, it is 3 times. So girth is 3 times the diameter. So we have to take care while taking the girth of a tree, as the relationship is 3 times the dph. So tree stems are not truly cylindrical. They are not truly cylindrical like this. If you see, tree stems are not truly cylindrical like this, because taperness occurs at different rate. You can see how the taperness is occurring at different rate from base to the top, and it differs from species to species and different situations and locations. If tree is a complete cylindrical, it would be very easy for us to measure the volume of a tree, but it is not like that, because here we will be considering d cube, a cubic diameter, by tapering from base to the top. This is a tree, and tree is never a cylindrical like this. It is never a cylindrical. But the calculation when we do, we have very less option to climb the tree and get the exact figure at different diameter. So let's understand first about the volume, how the volume is being calculated. So there is a very simple formula for volume. Volume is equal to S into L. L is the length and S is the cross-sectional area or sectional area. This sectional area, this entire section is called S. So to calculate the volume of a cylinder, because it is very fixed, so it is very simple, we can get the accurate result. Okay. So sectional area, already I have explained how to calculate the sectional area. We also say pi r square, or we can say pi d square of 4. So this is the diameter here. We can see this is the d. Okay. So we can calculate it this directly. This sectional area will calculate it. So here we get in two-dimensional. This square means it is centimeter square or meter square, we can get it. But when we take this length, we have three-dimensional. We have three-dimensional. So whatever result we'll get in or cubic meter or centimeter, like this we'll get it. So we can calculate very simple. But when we take it for tree, the tree is slowly tapers down. So when it tapers down like this, so it is very difficult for us to calculate, because we have to assume this is the extra volume. If we take this sectional area here and we take this length, so we'll consider this as a full volume. So this is the overestimate.
So tree stem involve complexity in stem forms and irregularity in cross section and basal area. Hence simple mathematical equations is impossible task, because trees is never a circular. It may be irregular, you can see irregular, or it may be ellipse. When it is an ellipse, we take it at the right angle to dia, that is one is minor axis and one is the major axis. If we take it dia, and we can take radius also, so we can calculate that one. So there is an error involved in assuming the tree as a circular, as Chaturvedi MD 1926
he has made a calculation of measurement of cubical content of forest crops published in Oxford Forest Memoirs. The selection of the tree diameter or girth is seldom circular. He says it is seldom circular. Rather, it sometimes approaches to an ellipse. It approaches sometimes like an ellipse. Therefore, calculation of a sectional area requires two diameters, he says. One is major and minor axis. Okay, this is a major axis, this is the minor axis of a elliptical section. So Chaturvedi 1926 has quantified this error for an ellipse with A and B as semi-major, means this is semi-major and semi-minor axis, and or as a diameter also. So this is when I say semi-major and semi-minor, this is a semi-major. We can take this is a semi-major, from here to here it is a semi-major. We can say it is a A also, and here it is a, what do you say, semi-minor, or we can take it a B. This is a radius, we are talking of radius. So let's see how it has been compared by taking the constant. He has calculated one constant. On the basis of constant, we have calculated how much error it comes. So when it is a true area of the ellipse, it is pi AB. This is semi-major and semi-minor axis, pi AB, or we can say pi divided by 4 D1 and D2. D1 is major diameter or minor, D2 is minor diameter. We can say major axis and minor axis. So what is the error in assuming the tree as a circular? Let's see how it is. So let's take two ellipses. One is this, we can say it is a in softwood, we can say it is a compression wood. You can see everybody know about the compression wood. The rings are more wider is compression wood. When it is softwood, gymnosperm, and when it is hardwood, angiosperm, we can see these rings are more broader. Here we call it is a tension wood. Here a tension is been created. Okay, so this is normal, but here you can see the eccentricity is somewhere here, the pith is somewhere here, the eccentricity is somewhere here. So Chaturvedi has calculated the constant on the basis of the eccentricity. I'll explain you what is eccentricity. You can see the eccentricity is somewhere coming here and eccentricity somewhere coming here. So if eccentricity value is 1, then it is circular, but when it is decreasing from 1, it may be 0.93, 0.95, then it is bit ellipse. So we can see how much ellipse it is. So formula 1 says that pi AB, to calculate the true area, I am talking of true area of an ellipse. One formula is pi A into B, that is radius, semi-major and semi-minor, or radius we can say. Or we can calculate pi by 4 D1 into D2. D1 and D2 are diameters. So we can calculate, we can get the true area of an ellipse by this calculation. It's very simple. Now how much error, because every time your tree is not a true circle, it is mostly irregular or it is ellipse. So how much error it comes, and what is that formula we should take up which gives you the minimum error. So method 1, he suggested method 1, area of a circle based on 2 semi-major or diameter. Method 1 says pi A plus B divided by 2. It is something like mean. A plus B divided by 2, then whole square. Or we can see pi by 4 D1 plus D2 divided by 2. We can take diameter or radius, one and same thing. But this here, it is something like average, method 1. So error comes to be, we'll take this error, how much error as compared to true area. He says this much is that error, 2 by 32 into this constant. Constant he has calculated as this formula is given by the eccentricity. So next formula is method 2, that is pi A square plus B square divided by 2. A square means is a radius square, and this is also radius square of minor and major, but we do separately area for these and then separately area for these and then divide it here. Here it is square as compared to mean here. So similarly for dia, you can take dia also, pi by 4 d square 1 plus d square 2 divided by 2. This is method 2. Here we can see the error is something more here, 4 divided by 32 into the constant. The third one is girth. Now area of a circle based on girth is very simple. G square divided by 4 will get that area, cross section or basal area by a girth by this formula. And you can see now here the error is 3 by 32. So still it is less than the method 2, 4 by 32. So this is the error involved in method 1 is bit less as compared to the method 2. So error compared in method 1 is less, then we can prefer the girth one, and the last one is 4 by 32. So this is how Chaturvedi has quantified the error for an ellipse.
So we'll discuss about the key formulas and compare which is the best one to calculate the cross-sectional area, because cross-sectional area will let us to know about the volume of a tree.
How the method ellipse method 2, the error is double. So in ellipse method 1, this is the formula as we have seen, that by averaging 2 diameter, that is pi by 4 d1 plus d2 divided by 2. This is somewhere we are taking what? We are taking the average here. Okay. Here in method 2, what we are doing, we are squaring d1 square plus d2 square divided by 2. Here it is square, means area separately, we calculate the area separately for each diameter, and then we average it. You can see separately it is calculated, then average it. So ultimately it becomes a double here. So for example, if we take an ellipse, this is an ellipse. So if we take an ellipse, and this is we can see if we take one diameter here, so it will ultimately become overestimate, and if we take this small diameter, then it will become underestimate. So we have to take what? Average. When we take the average of major and minor, then error is bit less. But here we do it separately and then we square it. Means here is something like we are doing double. So we can minus it. We can take this method like this first one, average one. we take it the average one here and minus by the true ellipse. This is the true ellipse formula for the true ellipse. This is the formula of true ellipse. We minus it and somewhere we get the calculation here. And here also when we take this d1 square plus d2 square divided by 2 and then we minus it by our true ellipse, somewhere we get it here the error to be more double. So error involved in method 2 is double the error involved in method 1. So it may not be a true circle. You can see a slightly ellipse. So there are different logs. You can see almost circular, and this log is very irregular. You can see here. So let's measure the area of this log. First of all, let's make the axis where 2 diameters. We'll mark for 2 diameters. Let's mark one here, the center. This may be the major axis and exactly perpendicular. This will maybe the minor axis. So here the major one comes to be 35.90 centimeter. $33.50. Let's take the girth also. Girth of this disc, 109.10. So we can also take the area by digital planimeter. This is a digital planimeter. With this planimeter we can take by seeing this lens and marking here. Readings will come here. Either we can take a graph paper. So that is, everybody may not have a digital planimeter. On the graph paper also we can measure the cross-sectional area. So we have to just invert it back and we mark the circle. We'll mark the circle. After marking the circle, we can either use by graph paper to take the area, or we can use the planimeter also. By planimeter, we have to just see with this lens and then we have to move it with this circle like this, and the reading will come here. So everybody may not have this planimeter, so we will be using this graph paper.
So eccentricity, what is eccentricity? It is the ratio of the diameter perpendicular to the longest diameter What does it mean? It means, let's take this is the longest diameter, and this to the longest diameter, what is the perpendicular one? So this is the perpendicular one, this is the perpendicular one. So that is the ratio we'll find out. So how we will do it? Eccentricity, suppose we have the longest diameter. This is the longest diameter. We have 35.90 and the perpendicular diameter is 33.50. So we will divide 33.50 by 35.90. So we get it how much? 0.93. Now what does 0.93 indicates? It has a value from 0 to 1. So closer to the circular shape it will be 1. So if it is a very circular, true circular, when it is a true circular shape, it will be 1, but as it is towards the ellipse, the value will decrease, like 0.99, 0.95, 0.91, 0.80, 0.60. So deviate away from the 1, lower the value from 1, it will be more to the ellipse. So this is how to calculate the eccentricity. So here we are getting 0.93. So this is a graphical method. In graphical method, we will calculate the cross-section area by a graph taking 1 centimeter to 1 centimeter. So let's calculate how much is the area of this cross-section of this log.
Now we will be counting this. This is 1 centimeter by 1 centimeter. If you see the graph, it is 1 centimeter by 1 centimeter. So each square will be 1 centimeter by 1 centimeter. This is 1 centimeter into 1 centimeter. So 1 centimeter into 1 centimeter is equal to 1 square centimeter. This is for each block. Now we'll count for number 1, full, which covers, and number 2 is partial, more than half, or half, which covers. So we'll count it. So like this is more than half, we'll count 1. We'll not count this, is less than half. This is also nearby, less than half. This is more than half, 2, 3, 4, like this will count. So we'll mark it first, which is more than half. We'll leave this one. This is all borders, first we'll do it. Counting of borders, which is more than half. 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61. So 61 is partial. Then we'll count for the full. For the full, we have to count the entire one. We'll count it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 502, 503, 504, 505, 506, 507, 879, 880, 881, 882, 883. So full is 883. So we'll plus it. So it comes 449. So we comes the area comes to 944 square centimeter. This is the area.
So this is a digital planimeter. So digital planimeter is also very handy, and direct reading we can get it from here by moving from this lens. Suppose this is that area, we'll pass the lens and we'll move this lens, and from here to here, and we'll come back to the same point. We'll get the cross section area either in square centimeter, either in meter square. As per our requirement, we can select it from here, the scale. So we get this calculations of this log by graphical method, by this true ellipse, and by ellipse method 1, ellipse method 2, and a girth method. And let's see which is more suitable for the selection.
So here we got the results of the dia for calculation of the cross-sectional area. So we are getting here the major axis of the diameter, that is 35.90 centimeter, and the minor one is 33.50 centimeter. So when we consider the semi-major and semi-minor axis, that is the radius, the semi-minor is A 16.75 centimeter and semi-major radius B 17.95 centimeter. So the authentic way, what we do, what we have done as shown in graphical method is more authentic. What we have done for a cross sectional of a log for comparing the error. So we are getting here 944 square centimeter for graphical method, which is closer to the true value. So we have discussed the first as a true ellipse, that is pi AB. We also say it as a radius of semi major and semi minor axis, that is pi A into B. So we take it this A into B, and as after the calculation with this formula, we are getting 944.93927 as a true ellipse. Then when we got it from ellipse method 1 by averaging, that is A plus B divided by 2, averaging, and then we did squaring, that is 946.0707, and then ellipse method 2 by separately taking the area, and we are getting this 947.20212, and the girth G square divided by 4 pi, we are getting 946.8147. Now let's compare and see the error. This calculation makes it very clear that double the error is in ellipse 2. So when we see this one, let's see the ellipse method 1. The difference with this ellipse method 1 graphical comes to 2.0707, and the difference with this true ellipse comes to 1.1314. This is the difference. Let's see, compare with the true ellipse with ellipse method 1. So this is the difference. This much error is coming, this much more it is coming. So when we do with ellipse 2, so it is, you can see, almost double, 2.26. It is 1.13 and it is 2.26, because when we minus it with this 2 ellipse here, it is almost double, and when we minus it with the graphical, it is 3.2021. So we can see here that with ellipse method 1 it is 1.13 and here is 2.26. So it is almost, we can see, double is here. So when we do it with this girth method, G square divided by 4 pi, when we calculated it, so we got this value, and this value when we minus it with true ellipse, we are getting 1.8752. It is still less than this method 2. So we can prefer ellipse method 1 first if it is properly taken by caliper. This is by caliper method, and this is by tape method, girth method. So everywhere we are not able to make the very accurate with the caliper. Sometimes it may be tilted, or many precautions we have to take. We can prefer girth also, because error is still less than this method 2, 1.8752.
So this is a summary of the entire calculations, and let's understand where the error is very less and which is more handy, and which formula is better to use in forestry.
When it is a circle, a formula is pi r square or pi d square by 4. Then calculation is square of radius of semi axis or diameter. This is by your radius, and this is by your diameter. When we take radius, for calculation of basal area, will take pi r square. When it is a true circle, so it is not possible for all the trees being a true circle, and the formula with the diameter is pi d square divided by 4. Now when we take a true ellipse, that is pi AB, this is a radius. So product and multiply of semi major A and semi minor B axis or radius, we get this by your true ellipse. So error is almost negligible or no. Now this is suggested by the least error by ellipse method 1 by averaging. This is the formula already we discussed. It is by averaging the two radius semi axis, that is A and B. So it is a radius by averaging. What it gives? It gives area close to the real basal area or true ellipse. So it is more acceptable, as given less error is comparative to your ellipse 2. This is more acceptable. Then ellipse 2, it is separately for A square, we calculate the area, separately for B square divided by 2. So calculating area of each radius or diameter and then averaging it, either this radius, either diameter, it gives an error, double the error involved in ellipse 1. So it is double the error here, ellipse 1. So this is more error as we take this formula for calculation of basal area ellipse 2. Girth. When we come to girth, it is g square divided by 4. So girth is what? This is a tree. Okay, we take the entire girth from here, entire circumference. Length of full circumference or perimeter is approximately 3 times the diameter, we call it. So we take the entire girth here. So what we get here, when we take the entire girth, this is the entire girth, so it is square divided by 4 pi. Error by tape girth is slightly more than ellipse 1. So it is slightly more than ellipse 1 as in calculation we have shown. So it is practically feasible. Due to calipered measurement need accuracy, it is more handy. So if we avoid personal error, then it is more feasible in use than ellipse 1 method, because ellipse 1 method is by caliper. So here we have to take more care, because caliper we have to make it right angle and we have to see the arms and many things we have to take. So it is not more handy, but it is more less error if it comes. But all the trees, sometimes trees are so big, in caliper doesn't fix it here. So girth is more handy as compared to ellipse 1, whether it is close to ellipse 1 in error, because more accurate is ellipse 1 than is girth. So error by tape girth is slightly more than ellipse 1 and practically feasible due to calipered measurement need accuracy, because calipered measurement need accuracy. Here we have to just make it perpendicular here, not tilt it here. So that is what we have to take.
So we have to take some precautions while measuring the diameter for cross-sectional area, because a slight error may cause overestimate or underestimate. So for example, when we consider the basal area, we should go for a right angle. If we don't go for a right angle and we slightly turn it, either it will be underestimate, either it will be overestimate. For example, if we take it only one dia from here, it may be underestimate because it is the minor axis. If we take the major axis, then it will be overestimate in that area. So we have to place at the right angle. This is very important precautions when we use caliper. Secondly is the arms. It sometimes get displaced. If it is displaced inside here, we get overestimate, and if it is displaced outside and the scale goes inside, is underestimate. This has to be taken care. Not only this, when we place in the angle in a tree, it should be right angle to the axis of a tree. Straight, it should be right angle here. Otherwise, if it is tilted to the angle theta, so what will happen? Again, we'll get overestimate. So for this precautions and how to take the diameter, please refer to the video lecture of Mensuration 3. So lecture number 3 has the detail of taking care and taking by the calipers and by the tape and the precautions to be taken up, because a slight mistake, a slight error in taking the dia either with the caliper or with the tape will cause a lot of error in calculation of basal area, which is dependent for the volume calculation. So this is the precaution of the tape, this is the correct way, and this is the incorrect when it is tilted down. So that is also overestimate. So tape should not be old also, because it is elasticity and expansion will happen. It should not be twisted or lie in a plane perpendicular to the, it should lie perpendicular to the axis of a tree and not be twisted. So because that is very, very important to take care with the tape. So ultimately we have to go for the cross-sectional, and a tree is never a cylindrical, it is tapered slowly. Not only tapered, it may be ellipse, it may be irregular. So we have to take care making it at right angle when we take major axis and minor axis. If it is a caliper and if it is a tape, we should put it in a right angle and perpendicular. It should not be tilted. So what we prefer as the calculation and summary, we have come to the conclusion that ellipse 1 method is more better, because averaging the two radius of semi-axis, that is radius A and B, gives us more closure, more nearer to true ellipse. If we take care of the precautions as caliper is been taken in a right direction, in a right angle only. But when it is not very much feasible with the caliper, girth is more handy and it is the second option, but still closer to ellipse 1 and it is still better than ellipse 2. So we can also take it as a girth, which is more handy and more better. Thank you very much. Keep watching for forest mensuration.